In this recording, we will discuss the exercise 3 given on the slide number 35 of the sampling distribution of mean. This problem is related with the previous problem. It was exercise number 2 as we solved. The population is same here as we did in the exercise number 2. But some differences are here. What that differences are, we have to find the probability random sample of size 36. Here the random sample size is large, 36 sample size we have, while in exercise 2 we have the random sample of size 4. So we have a large sample size here. One difference is this, which is a major difference. And the second difference is we selected the sample by with replacement. As we did in the exercise 2, the sample was drawn by without replacement. Due to the without replacement, we use the theorem of without replacement with the FPC for finding the variance of the sampling distribution of mean. But here in this problem, we can use the advantage of with replacement for computing the variance of the distribution of mean. So I am going to take some material from the slide number 2, which I already computed in case of the population mean and the population variance. Now you can see that the population mean is 4 and the population variance is 5. It was the requirement here to construct the probability distribution of population. So this is the probability distribution of population that we have constructed right now. Now with the help of this, we have to compute the mean and the variance of the sampling distribution of mean. So according to the theorem, sampling distribution of mean is same as the mean of population, and the mean of population was 4. It is equal to mu according to the first theorem. According to the second theorem, variance of the sampling distribution of mean in case of sampling with replacement, it is equal to sigma square upon n. And in this case, the sigma square is 5 and sample size is 36, which is given here. We have a 36 here. So this is the variance of the sampling distribution of mean. Now you can calculate the standard error. Standard error is what? Standard error is the standard deviation of the sampling distribution of mean. It is equal to sigma x bar. Sigma x bar is equal to square root of 5 upon 36. Square root of 5 upon 36 is the value of the standard error. Now I am computing the value of 5 upon under root 36. This standard error is equal to 0.3726. Now we have the mean and the standard deviation of the sampling distribution of mean. We can find out this probability. What probability is required? The probability in between 3.8 and 4.5. X bar lies between 3.8. In contrast of the exercise 2, in exercise 2, we have probability was given, but we have to find out the limits of the two values in which the probability will be at least 75%. Here the probability is not given. In this problem, we have to calculate the probability in between these two numbers. So the major difference is what? Major difference is that we used Chebyshev inequality, because according to the Chebyshev inequality, this percentage 75% will lie between mean minus plus 2 sigma. But here we can use the central limit theorem to compute this probability. According to the central limit theorem, if the population is not normal, as we have in this case, but if the sample size is large, then the sampling distribution of mean will be approximately normal. So I am using this theorem here. We have to calculate the probability of x bar lies between the two numbers. What that two numbers are? These two numbers are 3.8 and 4.5. 3.8 and 4.5. Now we have to convert this into the Z. Then we will use the normal probability table to find out these probabilities. So this can be converted into Z according to the central limit theorem. 3.8 minus 4. 4 is what? 4 is the mean of the population, or the mean of the sampling distribution of mean, and the standard deviation of sampling distribution of mean is 0.3726. So this is 0.3726. Lies between x bar minus mean, or the mean of x bar, both are similar, and standard error sigma x bar. This is the standard version of the z-score. On the right side, we have 4.5 minus 4 divided by 0.3726. Now we have to calculate these two limits. In between that, we have a z here. So this can be written as z, because the middle term will be z. And then we have to calculate the two limits, lower and the upper limits. And then we will use normal probability table to calculate this probability. And this is equal to minus 0.536. And the upper limit is equal to 1. It is equal to 1.3416. This can be written as probability z less than 1.3416 minus probability z less than 0.536. This can also be written as f 1.3416 minus f 0.536. Now the probabilities are taken from the normal probability table. In the normal probability table, 1.34 is this. This is 1.3 and this is 4. The 1.34 is represented here as this is 0.04 and this is 1.3. So actually this is 0.9099. 0.9099 is the first value, 9099. And the second value will be what? Minus 0.536. The minus 0.536 from this table, minus 0.3, 0.3. 0.536 minus 0.5 is this, minus 0.5 and 3 minus 0.536, 0.5. This is 0.5. And 36 means what? 0.53 or 0.4, whatever we can take. 0.5 and 0.53. This is the number. In the column number 4, 1, 2, 3, 4. This is 0.29, 0.2981. 0.2981 is the next number. Then we have to calculate the difference. This is equal to 0.9099 minus this is equal to 0.2981. This is equal to 0.6118. So what we can say here, we can say that in between 3.8 up to 4.5, 61.18 observations lies within these two numbers.